Good morning, everyone, or good afternoon, or good evening. I'm Rado Kalinescu. I'm Program Chair of SEFM, and I'm pleased to welcome you to the second day of the conference and to introduce our keynote speaker today, Sebastian Uchitel. Seb is a professor at the University of Buenos Aires. He is a principal investigator of the Argentine National Scientific and Technical Research Council, and he also holds a readership at Imperial College London. Seb's research interests are in behavior modeling, analysis and synthesis applied to requirements engineering, to software architecture and system design. His focus in this research is in particular on the use of synthesis at runtime to support system adaptation. He is an associate editor-in-chief of Transactions on Software Engineering and has held additional editorial responsibilities at Communications of the ECM, the Requirements Engineering Journal, the Science of Computer Programming Journal. He was program co-chair of ASE in 2006, of ICSE in 2010, and he was General Chair of ICSE in 2017. He has also served on the board of directors of the Argentine National Oil Company and has been an advisor to the Chief Cabinet Officer of the Province of Buenos Aires. Seb has received multiple prizes and awards, of which I will only mention a few. He received the Philip Leverhulme Prize, the Konex Foundation Prize, the Houssay Prize, and he is a member of the Argentine National Academy of Exact Physical and Natural Sciences. As I mentioned, his research focuses in particular on the use of synthesis at runtime to support system adaptation, and his keynote talk today is precisely on this topic on controller synthesis for adaptive mobile robots. Whenever you want to start, so thank you.
Great, Radu. Thank you very much for the introduction. Hello, everyone. Very pleased to have a chance to tell you a little bit about some of the ideas we've been working on these last years. Not so pleased that I can't see you in person, as I'm sure you all are, but this is what we have and this is what we're going to live with for now. So I'm going to share my screen. Just let me get that going. This should work. Okay, I think you're seeing my title screen now.
That works perfectly. Thank you, sir.
Great. So, well, I know conferences and well, not only conferences, but working life and personal life these days is mediated through screens a lot, and we all find it very hard to keep our concentration. And so I've prepared a very short talk to start. So essentially, I've been interested in using controller synthesis at runtime, meaning that systems that do synthesis while they're executing and use those controllers. And I've been working on engineering adaptive mobile robots and found quite a few problems in applying controller synthesis in that domain. So we've been working on new abstractions, design, specification language to solve them. That's what my talk is about. So thank you. Thank you for listening, at least reaching this point. So now I'm going to give you the slightly longer version. The longer version starts with the present. So perhaps some of you do Christmas and get a present, or maybe you buy yourself presents once in a while just because you deserve it, of course. And this present, of course, is a UAV, an unmanned aerial vehicle or a drone, and you buy one of these, and what you do is, what you're probably going to do is go out somewhere and use it with a remote control. So what does that mean? That you have this device in your hand, and you're going to be pressing and pulling the levers of the remote control, and that's going to be sending some commands to the UAV. And these commands, which will look something like you've pushed the lever forward for a certain number of seconds, will be interpreted by the UAV as a move forward, and the software on the UAV will move the propellers with certain force in order to actually achieve some movement of the UAV for some distance, right? The UAV will be sending events and video back to your remote control, mainly video in these devices, so you can see what the drone is seeing. And most of the magic, most of the interesting stuff happens here at the UAV. I'm assuming you can see my cursor. Is that okay? Is that true?
We can see the cursor.
Great. Okay. So most of what's interesting happens here in the software happens here on the UAV. So the UAV consists of some hardware, of course, but it also has some sensors. Well, it has sensors and actuators. The sensors are part of the communication with the remote control, but of course they also can measure the altitude, maybe the wind, and so forth, and has the actuators, which of course mainly are the propellers, but can have cameras and may have a gripper and all sorts of things that come with these drones. But most importantly, it has a lot of software that implements some feedback loops that can take a command like move forward and actually convert that into quite a complex mechanism in which the actuators and sensors are used to figure out how much force needs to be applied to different rotors to actually get to move forward the right amount. So there's a lot of work here, and this is work that belongs mainly to the world of control engineering, where they study dynamic systems with continuous variables and see how with these feedback loops they can achieve a particular goal, like moving the robot 2 centimeters forward. So this is, of course, a lot of fun to use, but of course not very useful in terms of automating tasks. It falls rather short in that sense. And so if you want to automate some tasks and have this UAV do something more interesting than just reacting immediately to the commands that you're sending it through the remote control, you might use a mission planner. Now, this is a screenshot of a mission planner that belongs to the suite of tools that come with the ArduPilot open source project, in which there's a lot of interesting tools that you can put together to control your brand new drone. And this tool here works in which you can see a map, a satellite map of where you are, and you might click on this map to put some locations where you want your drone to go. And here at the bottom, you'll get these waypoints which are what you clicked on in the map, and you can associate to these waypoints or between these different lines some commands of what you might want the drone to do there. So you might want it to go up or take a picture, or well, whatever your drone can do, you can apply a new command here. And this is how you write in a very simple way a mission that when you have finished and press play, if you like, what happens is something of this sort. So you drew your mission with the mission planner, and the mission planner will talk to the computer, will use the computer on which it's running as a ground control station, which will be sending commands to the UAV and getting information back. And so what we've replaced the remote control with this mission planner that essentially is a very simple programming language, programming tool, graphical programming tool, right? So if you wanted to, a typical UAV mission, which is to survey an area, for instance, to be able to produce photographs that you're going to put together into an orthomosaic and then analyzed perhaps to see how crops are growing, or if you lost any cattle, or if you want to see if there are any, if you're looking for something in some area. Well, this is the kind of mission that you would write. And you can see here that it can be a bit cumbersome, because now I need to take 40 pictures. This is a very small area. I need to do all these clicks. I need to put in down here the different things I need to do at each waypoint. And of course, that's not very convenient, but also this way of programming missions doesn't let me do a lot of things that I might want to do. So all the actions are tied to waypoints, and I can't really tie an action to react to something that I might be sensing on the way. So, you know, if while traveling between point 3 and 4, something happens, maybe I want to program some action and I can't with this scheme. The business logic is very tied to the waypoints, if you like. There's a fixed trajectory. I've fixed the trajectory this UAV is going to do. Maybe the wind changes and I want to traverse this area in a different way, and I can't because I've already programmed it. Maybe I want to decide where to go based on the things that I see, and I can't do that either here. So in conclusion, there are a number of limitations that have to do with limited reactivity. I can't really have a true reactive behavior specified with this kind of tool. And if I want to have some more reactivity with my UAV, I'm going to have to perhaps program. And so, of course, you can write your programs, and this is what a little bit of some of the code that I took out of the ArduPilot project. And of course, you're going to need some expertise to write these programs. You're going to have to be careful. It's very easy to make mistakes here. There are lots of events. You have to consider things like race conditions because of all the different processes that are running concurrently on the drone that might produce events that you need to deal with. And you're going to struggle with correctness guarantees. Verifying this is going to be hard. Testing it is going to be hard too. In fact, there's a lot of tools that help do simulations of these kinds of these programs to try to give some assurance. And it's certainly a way forward, but of course, as I said, expertise, it's error prone, and it's hard work to get some correctness guarantees here. Ultimately, it's you that's going to be producing a mission plan in terms of the program, and that program might run on the ground control station instead of the plan generated with the mission planner in the graphical form, or it might actually sit on board the UAV, but ultimately it's going to be communicating either through the airspace or through cables fixed directly onto the UAV with commands and events, like I said before. So of course you might have a more complex configuration here. You might have your program that's sitting on the onboard control station, a computer that's sitting on top of the UAV and actually flying, but you might also have a ground control station where you're monitoring what's going on. And you might also have your remote control, because in many countries, as in Argentina at least, it's mandatory to have someone ready to take control of the UAV in flight. Fully automated flights are not allowed. Okay, so that's another way, but of course this is a hassle. It's a lot of work, and perhaps you can just buy the software you need. And there's a lot of software that's really very cool, works very well for all sorts of tasks. This is a photo. Well, it's some kind of image that's trying to tell us about this drone that can do some surveying of different aspects of the fertility of the soil for agricultural reasons. And these tools, as I said, work very nicely, but they are a problem. They're a problem because sometimes you have to buy the hardware with the software, and it's proprietary hardware, it's proprietary software, it's proprietary data. You can't really modify it. You can't even access the data you're picking up to do your own processing. You have to do it through the tools provided by the vendor. And this is a huge problem, right to repair goes out the window. Sometimes you get vendor lock-in, you have no flexibility to change and adapt the software for your specific needs. This is a big problem for instance, small farms and developing countries in general. So this solution has its problems. So this is how we come to the idea of automated mission planning, which is an idea that's been moving along for a while. The idea is to address this in a different way, with of course its advantages and disadvantages, but it's a different way in which you provide, rather than a mission plan, you provide a mission specification. So not how to solve the mission, but what it is that you want to achieve in the mission. And then some piece of software, which I haven't given a name deliberately because it changes from approach to approach, will produce some kind of plan. It could be some software, it could be ultimately some executable form of a mission that again is going to go through this interaction with UAV. Now, what we've been looking at is putting in here technology that's sometimes called controller synthesis, and it's actually called many different ways in different communities, but I'm going to talk a little bit about control synthesis in the most abstract way I can, and try to go in as least as possible to the specifics of how we do controller synthesis, because I want to talk about some ideas that I think go beyond one particular way of doing controller synthesis. Anyway, so what is this notion of synthesis? The idea is that you have a program that's going to take three inputs. It's going to take an input, which is the phenomena that can be controlled and monitored by the controller. And I use the word phenomena because sometimes the phenomena is referred to events. Sometimes these are variables. It can vary. But the idea is, what can the controller do, and what can it hear? What can it listen to? And the other input are the assumptions about the environment, or the assumptions about the phenomena. What can this controller that we're going to build assume about the relationships between these controllable phenomena, these monitorable phenomena, and that it can use it to its advantage to achieve a particular goal it has to achieve. So the idea of this controller is it's something that can execute and that can monitor the environment. We can monitor the phenomena of the environment that we specified, and can act upon it usually through some mechanism, using some strategy that is guaranteed to achieve the goals, as long as the environment behaves according to the assumptions. So no matter what the environment does, as long as it follows these assumptions, then the controller should and must be able to achieve its goals. The easier way of thinking about synthesis is thinking of it as a two-player game. So two-player games we understand very well, especially when they're about boards. And so one way of thinking of synthesis, for instance, is thinking about the noughts and crosses problem. So the kind of phenomena that we're interested in is in putting pieces on the board, noughts and crosses. In this case, the controller is going to play as crosses. So those are the controllable phenomena playing these crosses, and the monitorable aspects of this problem that are being able to observe where the noughts are played. So the assumptions about this phenomena have to do with that you're expecting that there won't be two plays by the nought player in a row, that the pieces, once they're put on a place, are not moved, that there are only 9 places to put these pieces, and so on. And of course, the goal is to have 3 crosses in a row. And the output of this should be something that looks like a strategy of what to do for each possible configuration of the boards of noughts and crosses. What should crosses do? And that strategy should ensure that if indeed crosses wins no matter what, as long as doesn't, for instance, play twice in a row or starts moving things around. So a synthesis problem can give you two results. It can say, actually, there's no way of winning, and we call that an unrealizable control problem, or it might give you actually a strategy for winning. Now, what is winning? Well, if you ask for noughts and crosses, I want a strategy to win, of course, synthesis will tell you there is no such strategy. Anyone that plays this game and knows how to play it knows that if your opponent knows a little bit of how to play this, there's no way you can beat your opponent. The best you can do is never lose. So in fact, if you put as a goal, rather than achieve 3 in a row, your goal is avoid your opponent achieving 3 in a row, then indeed your synthesis will give you a strategy to avoid that. That is to never lose. So the whole point of synthesis is that we want to design one algorithm that can input many different kinds of games specified in one particular language. So an algorithm and one language for describing rules, such that for any set of those rules that define a game, you will get a winning strategy if it exists. So you can code noughts and crosses, chess, Go, whatever game you like, and your synthesis algorithm should be able to solve it. So synthesis is quite different from machine learning. And it's important to say this because people tend to go that way as soon as you talk about chess or Go. In synthesis, you put in the rules of the game and you synthesize a strategy that's guaranteed to win. This is quite different in a deep learning approach, for instance, in which you might feed your learning engine with lots and lots of matches of chess rather than the rules of chess. And the result is a very good strategy of how to win, how to play chess that might win against any possible, every opponent you give it to. But you never know if you might give it an opponent for which that strategy might lose. In a sense, it's a good strategy, but it's not guaranteed to be a winning strategy. So that's an important difference there. And of course, it's an important difference in terms of scale. The truth is that with synthesis, we can solve tic-tac-toe or noughts and crosses, but we can't solve chess or Go. In fact, I'm not sure it's known that there is a winning strategy for chess and Go. I'm pretty sure there isn't. But anyway, we can't answer that question either. Of course, we can do things in the middle. We can do things that are bigger than noughts and crosses. We can't do chess and Go. So how does controller synthesis work? Well, you need to define language for describing your assumptions and your goals. You need an algorithm that can process that, and you need to decide what your output's going to be. The output typically can be thought of as an automata or a tree that tells you for each configuration of your game what to do, or an automata that encodes a tree pretty compactly in many cases. So the three different schools that have looked at this problem in different ways, but essentially are thinking about the same problem. One is what's referred to as reactive synthesis, and here the phenomena that we control or monitor are propositions that can be read or written by a controller, and the assumptions and goals are described as LTL formula. The game that's assumed to be played between the environment and the controller is a game that is played in strict turns. So the controller will pick a whole, will read the readable propositions, and based on what it reads, it will decide what to write in its own propositions or variables, and then it's going to be the turn of the environment that will look at what the proposition's valuation is, and will change the valuation only for the readable propositions, the ones that are only readable by the controller, but of course writable by the environment. So these propositions are split. The two players take turns. In each turn, each player can change as many propositions as it wants of the ones it can control. And of course, this setup, which has its origin in synthesis in the hardware domain, and really fits well with a shared memory design, in which you have processes which have a shared memory and are communicating via that shared memory. Supervisory control is a different approach to this, and takes very much a message-based communication approach to thinking about a controller and a system that's under control. So now we have events that are controlled or monitored by the controller. Our assumptions and goals are described using communicating automata. So that's automata and some notion of parallel composition or synchronous product. We have marked states and illegal states in these automata. And typically the property that's looked at is a property called non-blocking, a non-blocking property, which essentially says that the controller must ensure that it is always possible to reach the marked state. Not necessarily that it will be reached, but there is a way in which that marked state will be reached in the composition of the automata describing the environment. So this game is quite different from the previous game, because here we have an asynchronous execution. The controller can play several might play several environment controlled events in a row. The environment may also do that, and more importantly, we can have things like race conditions, in which the environment may beat the controller as many times as it likes in some race. So this is similar problem, different way of specifying, but some pretty fundamental differences in some of the assumptions of how this game is played, and so what is the interaction between the system under control and the controller. A third area that's looked at this kind of problem is referred to as AI planning, and the way in which the problem is described here differs again from the previous two. Here we have controllable actions that have non-deterministic outcomes. The non-deterministic outcome is what is decided by the environment, and of course, which controllable action is taken is decided by the controller. So these actions have pre and post conditions specified over propositions or fluents, and typically, at least initially, goals were about reaching a particular fluent valuation or recurrently, infinitely often achieving a particular valuation. Here again, we have this lockstep execution where the controller chooses an action to do, and then the environment chooses which of the possible outcomes is going to happen, and then again the controller chooses again. And of course, because the post conditions of the actions can affect several variables, in a sense, many things can happen per turn every time an action is taken. So these are three very different ways of approaching the problem. We, of course, decided to do things differently from all three. We took an approach that is, I would say, a natural evolution of the way software architectures are modeled and reasoned about. So we describe the environment using process algebra. Essentially, we have a language which is can be compiled into a label transition system or a composition of them, and these typically would be processes describing process algebra that relate to different components in the software architecture that would be composed, and you would check if a property holds and describe perhaps in an LTL. In synthesis, rather than building a term in our process algebra of the whole system, really what we have is a system where one component is missing, the controller. And what we'd like to figure out is what should that final process look like for the composition of the entire system to actually satisfy the formula. So here, this is what we're looking at. We're looking at E is a description of the environment of the controller. This might be a composition of many other processes, just using E to simplify. And what we want to do when we do synthesis is compute a C, a controller, such that when composed in parallel, satisfies the goal given as an LTL formula. And the other thing that's important is that C actually conforms to this, conforms to the interface described as a set of controllable events. So this means that C should never block E in anything that's a monitored event for the controller. And this amounts to essentially some notion of legality as in interface automata. So that's really my introduction and all I'm going to say about how these techniques for synthesis work. The main point now is that I want to come back to UAVs and place here some notion of controller synthesis. So I'm going to have mission specifications, and I want to synthesize a plan that's going to run on board the UAV. So to be able to do synthesis for mobile robot missions, you need to be able to discretize this environment, this world that has continuous variables, the speed, the location of the UAV, the height, all these things that the real domain of these variables is in the continuous world. You need to bring them down to a discrete and pretty finite world. And so you might think of binary sensors that respond if some amount is above or below a threshold rather than the actual value. You might have controllable actions with a restricted finite number of parameters. So you might have go to position 1, go to position 3, move to height 5, and so on. And of course, you need a workspace or an arena for the mobile robot that's been discretized. You need to bring your R square to maybe a grid like we're seeing here of a finite number of locations. And once you do that, and this is what people do when they're synthesizing controllers for mobile robots, you can now apply this scheme. So you're going to have to discretize your world and then write a mission, a specification for your mission in terms of that discretized world. And you're going to produce with the synthesizer a plan. And that plan is going to say things like go to location 1. And that's that command, go location 1, is going to have to be processed by a hybrid controller. That's one way of calling this layer of the software that understands that discretization that you made and knows that go to location 1 is actually go to a particular region in the real world, and we'll deal with then moving there, moving the UAV to that position maybe by a number of smaller steps that guide the UAV in a trajectory to the perhaps center of that discretized location that you are calling location 1. So to give you a more concrete example, perhaps if you're trying to do some kind of survey, continuous patrolling for fire in an area, and perhaps these orange areas are the areas which are of interest to actually do the patrolling, then you might gridify, if you like, your space to be able to talk about locations A1 and B2 and etc. And you might write a mission specification that in essence says something like this, that the things you can do as a controller are go to an XY, and you can ask if there's fire at that location. You can take a picture, and the things that you can monitor are the fact that you arrive to a location and the answers yes, no to a question you made to the fire sensor. And the goals that you might write are things like, well, you can only go to an adjacent cell to the cell you're currently on, and you sense for fire, you should only sense for fire at the orange cells. You should only take a picture if there's fire, and these kind of are the goals or the restrictions and the properties that you want for your mission. And the kind of assumptions you'll have are things like, well, if you say go, then eventually you'll get some kind of notification that you arrived, and that the yes and no fire are actually responses to the question fire, and they don't happen in ad hoc time points. So these are the kind of things you're going to write. It really is looking at the control. Okay, so the controller is going to look something like this. So in this case, it's a controller that commands the UAV to go to position B7. So that's here. And then once it's arrived, it's going to go to C7. And once it's arrived, it's going to go to C6. And it's going to go take a little small trajectory till it reaches actually C5. And C5, which is this location here, is an orange location. So you're going to ask if there is a fire here, that's going to presumably take a picture. So these commands and events are really happening through interaction with this hybrid layer. So when you say go B7, this is going to be a command that comes here to the motion planner that's going to convert the B7, or in this case, the C3, into a particular position that's a target, and it's going to compute a whole bunch of positions on the way that they're going to help me get to that position, and send commands, control inputs to the feedback controllers of the UAV, that as it gets to each of these intermediate points, the motion plan is going to update that until it reaches actually the center of C3 or whatever it is. And of course, the fire is going to be a command that's going to be processed by some actual sensor, and it's going to be able to have to respond yes or no in terms of some threshold, as we were saying, on how to decide if there is fire or not, maybe temperature or something like that. So you can see here that this controller can be quite large, particularly if this discretization is large. If I'm talking about a big region here, then this is going to be quite a big controller, and this is going to be hard work for the synthesis, because the synthesis really is going to blow up in terms of computation time and memory, because the number of states is going to, the number of positions really produces a combinatorial explosion of the number of states that your game can be in. And so it gets really expensive to solve these problems as you add rows and columns, which is one of the big problems. And it's perhaps the big problem of applying these kind of techniques for mobile robots. The whole point of mobile robots is that they're mobile and they move a lot, and that it's very interesting to have significant control over where they move and what they do when they're at different places. So we're back to that square one of the mission planner, where I had to put all these dots, and if I have to put a lot of them, then it's quite uncomfortable and cumbersome. And now if I have to have a lot of discrete locations, then it's also quite a problem, but it's not for me, but rather for the synthesis algorithm, but ultimately it's a problem. So precision versus scale. If I want high precision on the locations I'm going to manage in my plan, then I'm going to have scale problems. And as I said, if you add lots of locations, you can have a combinatorial explosion of the state space of the synthesis problem you're trying to solve. And if you add on top of that, that your synthesis algorithms are not linear with respect to your combinatorial, to the size of the state space for most interesting properties, you have to go beyond that, then that's going to be very costly. So there's been a lot of work on how to discretize in efficient ways to reduce the number of discrete locations that you're going to have, and from these regions produce an adjacency matrix on which you can reason about when you're doing the synthesis. But this is simply not enough. I mean, you look at the literature on what these techniques are capable of doing. They talk about plans for hundreds of locations at the very most. But really, we need thousands of locations, not hundreds of locations, or maybe tens of thousands. So if you think about these missions like search and rescue, fire detection, surveillance over an area, or surveys in agriculture or forests and stuff, then you're looking at many locations. If you think of a drone flying at 50 meters, it's probably going to have a footprint of the footprint's going to be more or less linear, probably 50 meters. The photos you're going to take are probably going to be 50 meters wide and 50 meters high. And if you're looking at 25 square kilometers that you want to survey, then you're probably talking about 5,000, 10,000 locations. So we really need to push hard that boundary of how many locations, how many states we can deal with when we're doing synthesis. So of course we need more efficient synthesis methods, and there's a lot of people working on that, and we are doing that too. It's very interesting, very challenging, and there's a lot of things that can be done, but perhaps abstractions can come to the rescue. Perhaps we can do what we do in software engineering and try to find new abstractions which can also contribute, and maybe in a very significant way, in a big step, to the kind of missions that we can actually synthesize, in particular with lots of locations, which is where we got stuck when we tried to apply these techniques for our drones. So if you think about these missions, they all have requirements that look very much like what's in blue. So they're all saying for every location in my arena, if some condition holds over that location, then I'd like you to achieve for that location some specific property. So, if my if the location is in a relevant fire search location area, then I would like to achieve visiting it and taking a picture and informing if there's a fire, if the sensor says so, something like that. So all these missions can be described pretty naturally with a universal quantification over the location and a local goal over that location that's kind of independent from the rest of them. That observation led us to think, well, perhaps this way of thinking of hybrid controllers, because you look at the literature and every hybrid controller provides this kind of API. I want to go to a location XY, and I'll tell you when I've arrived, is not what we need. And perhaps what we need is a hybrid controller that can deal and hide away, abstract what locations we have, which locations are available in our arena, and just have some abstraction of like an iterator in which the controller can just cycle through the iterator and say, have you got a next location to process? And if there is one, yes, next, then I'll just go to that location. I don't care which location it is, just take me there. And then I'll do things at that location. And when I finished, I'll remove it from the iterator and say, I'm done. Just give me the next one. And I'll cycle through the locations in the iterator until I get, well, look, you've finished. You've reached the end of these this list of locations. And so if we had hybrid controllers, a layer on which we're going to actually produce controllers that can rely on this API, then we can get controllers that look like the one here on the top, which is quite different. If you recall, the first controller that I showed would say things like, go to the first, go to C3, and then go to C4, and then go to C5, and this iterator really is cycling over an iterator. It says, is there something in the iterator? Has next. If there is something in the iterator, this is state 3. Is it in one of the patrolling area? Is it a patrolling location? If it is a patrolling location, okay, let's go there. And once it's arrived, let's check if there's fire there. And if there's fire, I'll take the picture. If there is no fire, I won't. But after that, I'll remove that location and go to the next one. So here, as you can see, this iterator is really encoding a cycle. There's no magic there. It doesn't need to know the locations. It needs a hybrid layer that's a bit more sophisticated. It needs actions that are independent of a particular location. It's hoping that the iterator, or that the hybrid layer, is managing these locations in a correct way. The hybrid layer is going to have this data structure that remembers the locations that have been processed because they've been removed from the iterator. It has a current one, and it has a whole bunch of locations that are remaining. And every time it gets an action go next, for instance, what it's going to do is it's going to go to whatever the current this n location here is pointing to, and it's going to go to that location. So for the iterator, it doesn't know that it's going to C3, but the motion planner is still receiving go C3 as before, and it's going to do exactly what it did before. And of course, we have this new sensor, which is the current location, which is C3. So here is the next location the iterator I'm processing in the set of patrol locations of interest, and that's going to be solved here by the hybrid layer too. So we're making everything a sensor and dumping it into the hybrid layer to be able to have controls that are abstract with respect to the precise, what the name or what the precise location is. We're just putting into the controller what are the properties that we're interested in of a generic location. We don't care what the location is. If it is a P location, then we're going to go. If it's not a P location, we're going to throw it away. So this kind of architecture, well, it's an architecture first, because we're really requiring a new hybrid layer that provides provides more functionality and different functionality than what's usually provided. Lets you synthesize in constant time with respect to the number of locations. So it doesn't matter how many locations my problem has, I'm always going to take the same amount of time in synthesizing, which is absolutely great because there's no limit to the number of locations we can manage, at least theoretically, producing these controllers. Of course, there is an efficiency problem. The first thing that we did was we pushed down into the hybrid layer this trajectory planning that we had before, in which our controller up here encoded that we were going to do this route. This route here is now not decided by the controller up top, but it's going to be decided by this iterator, the order in which these locations are iterated over down here. So the order in which this happens is going to be crucial, and we're going to need an architecture that actually sorts this in some way. Sorts it in some way. And here is where you might have some scalability issues, right? Can you sort these things in time? If you've got millions of locations, is this feasible at all? Is the trajectory you're going to finally follow a good one? Can you actually solve that independently of the problem up here? And these are all good questions. And we believe that rather than a problem of delegating trajectories to this layer, it's actually an advantage. So really doing control synthesis here and trying to do optimization at the same time and having hard goals is hard. It is hard in terms of complexity, and it's actually not in many cases what you want. Most of the things you want to do in terms of deciding the order in which you go through these locations depend on runtime characteristics, like where the wind's coming from. So while you're flying, you probably want to fly crosswind. That's how you usually fly with these drones. Why? Because they're more stable, they turn more stable, they can take pictures in a more stable way. So you might prioritize the next location you're going to offer is one that's close, but it's also favors traversing perpendicular to the wind, traveling perpendicular to the wind. So this is what we implemented this, and the implementation was mainly to show that you can actually build this hybrid layer and that you can actually at runtime sort these locations in a reasonable way that will give you some good behavior. And so here we solved this classic, I would say, mission from this paper from CONICET, which they call Find Nemo, and essentially it's finding something in an area of interest, and here we're kind of doing something weird because we're looking for Nemo on land. We marked this huge area over 100,000 locations, and the areas of interest within that are the locations that correspond to land, and we had the robot find Nemo on land, and you can see there the trajectories. It's a fixed wing airplane, so it takes a while to turn, and that's why you see some loops that go outside land. But the point here is that we were able to synthesize controllers for an arbitrary number of locations for this mission, and actually the part that we delegated to the runtime or execution of the mission can deal with hundreds of thousands of locations, no problem. This is a simulation, I should say. We didn't actually fly a plane. We simulated the lower layer of the hardware. Was simulated using a simulator for these things. This is an actual flight we did in Patagonia. Patagonia is a good place for flying drones because there are not many people around. And we had it, again, we had this huge area of 30,000 locations. Nemo was actually this red target here, and this is the photograph of when the drone actually sees that red target, and this is the trajectory. So it was these are good results. So this is work we've been mainly showing at the in the robotics community, I should say, of how to engineer robots with guaranteed mission plans. So summarizing what I've said up to now, this is on top is what our iterator-based controls look like, and they have these cycles in which they're iterating over a set of locations essentially, and this is what typically a controller looks like in the literature for the same kind of missions, and where you explicitly are managing each location. And so we introduced this new abstraction called iterators, both into the language for synthesizing mission plans, but also this requires a change in the architecture, and this gives us constant time and space with respect to the number of locations, but pushes down the trajectory planning, right? As I said, and this has, this really has pushed the number of locations enormously. There is a problem with this approach that we've been working on, and it's I just want to show you, because I avoided showing you what the specification looks like for these iterator-based missions, and the reason why I avoided it is because they're rather complex. So you have to write things. You have to write requirements or constraints that actually refer to how the iterator is used, because now the controller manages, controls actions that are relative to the iterator, like give me the next one, remove the next one, etc. So you end up writing things like this: if there is another location, do not remove it from the iterator until it has been sensed for fire and reported if the sensing was positive. And the part that's not completely satisfactory here is that as a user, I'm having to now deal with this thing called yes, next, remove next, which aren't really part of my problem. I was interested in fires and not in iterators. And so, we pushed up the level of abstraction of our synthesis, of our hybrid controller API, but we're writing lower level specifications. So this is inconvenient, and you could argue, well, yes, if the lower level, if you really want to go low level, you might as well program the whole thing, right? And because you're rightly programming the iterator. So this wasn't very convenient. So what we want to do was go back to this notion of quantification, right? What I want to write things like this. For every location that's a pickup location, I want to infinitely often visit that location. And if it's always the case, sorry, and I've written these things in temporal logic just to give a feel for what these requirements actually look like, or the language that we're aiming at looks like. So it's always the case that if you're at a particular location, then you should pick something up at that location, and eventually there's a location that's a drop-off location at which you will be at, and at which you will do the drop-off. These are the kind of things that we want to write, and we'd like to write these specifications like this and have them translated into an iterator-based specification. So in a sense, translate them into a way of solving this using loops over these sets of locations. Because if we can do that, then we know we can synthesize that, and without caring how many locations you actually have in each set. And so this last step is constant time with respect to the number of locations. And if we can do this translation from this controlled quantified specification into an iterator-based specification, then we get a high-level description of the emissions that actually scales very well. Now, why do I refer to controlled quantified specification? Well, because you can write, it's very easy to write the specification with quantifiers and over sets that can't be solved with an iterator. And one simple example is a specification in which you manage to count how many pickup locations there are. If I can count how many pickup locations there are, then of course there's no way of writing a plan that's oblivious to the number of locations there are, because there are a fixed number, right? So this can only be done for problems in which there is a solution to the specification for an arbitrary number of locations in each set of locations. Here we've got two sets of locations, pickup blocks and drop-off blocks. So this led to a particular language with quantification placed in very particular points, and some conditions over the specification ensure correct and complete, that there is a correct and complete translation into an iterator-based specification. Of course, the semantics of this is very obvious, right? This is for all locations. This line over here is really a conjunction of all the locations in the pickup blocks, right? So the semantics of this language is pretty obvious, but the question is, can we translate that into an iterator-based specification that has exactly the same solutions as the original specification?
So you'll leave some time for questions.
Yeah. Oh, how am I doing with time?
Pretty much running out of time.
Oh, shoot. That was okay. Yes, I can finish. Okay. So why not quantify over other concepts then? Rather than locations, can't I do packages, people, cows? And indeed, it seems that this can be done. So we're working with people in the cattle farming area. This is Argentina. So what else are we going to do? And these people want to use drones to count the number of cattle they got in each pen every day, every morning. They want to identify each cow and apply certain things to each cow, perhaps measure the temperature to see if they have fever every day. And so these are the kind of things that you might be able to do with a drone and with universal quantification over these elements. So I didn't get to the end, but I did get to the end of a big part of what I wanted to say. So I guess this is a good moment to skip a lot of slides, if you bear with me. I'm not sure how to skip. Yeah. So my main collaborator for this for the work I've been talking about is Sebastian Uchitel, who's a PhD student of mine who lives in Bariloche and who's given me an excuse to visit many times down there and work with him, which has been a lot of fun. And I guess the summary, the TLDR that I said before is we started out building these drones. This is a handmade drone and flying them, putting plans on top of them and seeing what we could do and what we couldn't. And this led us to a whole different way of trying to address synthesis in this domain. So I hope you took something out of the talk, and yeah, we can do some questions.
Thank you very much, Seba. My most insightful talk. If people want to ask questions, and do announce in the chat or just raise your hand. But while people are thinking, I might start with a question of my own. So yeah, you mentioned quite a few times the challenge of synthesis because of the complexity. Now, I suppose some of that challenge could be taken away if you do not aim for the optimal solution. Well, what do you think about solutions that might combine maybe techniques such as machine learning to identify candidate plans and then use verification in combination with one of these heuristics, shall I say meta heuristics perhaps, to verify the plan and achieve perhaps something that is suboptimal but feasible? Or would that
No, I think that's certainly a way. That the problem is, of course, completeness. If you're willing to drop completeness, there's a lot of things that we can do, and I think we are sometimes too obsessed with completeness. So I think that's definitely a way. I mean, we're looking at things along those lines, particularly heuristic search, to avoid building the full composition of the environment, to find a controller that uses 2% of the state space, but before you run out of memory, building the whole composition.
Mm-hmm. Yeah, of course, humans do operate in a suboptimal way, but we kind of manage most of the time, perhaps less well at the moment.
No,
I think you had a question.
Yes, thanks for the talk. I had a question regarding, so basically, if I understood correctly, you introduced this iterator which takes over the entire planning of the route which the drone is going to take. Where's the difference? Why not just introduce a second controller just for the route planning, which can have its own specifications, right? It takes into account, wind directions, whatever you mentioned. And so essentially what this viewpoint, I think, would allow you, because currently you have these two layers, one controller, and you pull some specifications from the controller into the iterator. But if you view it as multiple controllers, there is nothing stopping you from maybe translating it into 7 different controllers, because you identify that there are 7 different parts which can work independently of each other. Absolutely.
Yeah, this is a very good point. I think the key is, if you like, that the separation of concerns. So the separation of concerns. So saying, the trajectories are going to be computed in a different way, and just give me the locations one by one. Now, that sorting component that I mentioned can be anything you want, and it can be it can be the result of an optimization technique. We've actually used several things there. We're actually using a discrete event simulator to simulate the whole architecture of the robot, plus the discrete event controller that's running the mission, to decide what is the best trajectory to follow. So you're actually looking into the future of what might happen to decide what is the best strategy. So you might want to simulate forward to see when you're going to run out of battery, to see if it's worth going forward or not, or maybe you just want to go back to the base. There's no point in trying to finish the mission, trying to get to some other point that you're never going to get there based on the amount of energy you have. So as you say, that separation is, we did it in 2 parts: the discrete event control synthesis part with the iterator, and the assumption that somebody's going to deal with the order in which those locations are produced. And you can use whatever you like there, very sophisticated techniques. Yeah.
All right, thank you.
Thank you, Patrick. So Grisel, you have the next question?
Yes, thank you. It was a very interesting talk. And I was wondering that given the specifications and how complex they can be. How do you ensure that the plans are what you expect?
Okay, so there's, I think you're referring, it's a good question. You're referring, I think you're referring to the problem of validation, right? Because we've replaced writing the program with writing a specification, and that specification is that when I write the specification, is it what I wanted to write or not? This is a problem of contrasting any formal description of something against your mental model, and that's obviously an impossible task because you're comparing something formal against something that's in your head. And there you have the same tools as usual, which are, you know, in our case, that they could be simulate the system with the control that you synthesized, or they could be look at the automata that you synthesized and animate it, or you quotient the state space and do some hiding to understand it, and all the things you can do with an automata to validate its behavior, you could do in this case. Plus, you could validate the whole system by animation or simulation.
Mm-hmm. So it's basically based on the user to know if it is what it expects. And okay.
Yeah. There's no way around that problem in software engineering.
That is true. And also another question / suggestion: have you considered multi-scale discretization to leverage the problem of precision versus state explosion that you mentioned?
No, I kind of think I know what you mean by that, but I'm not very sure. But you know, we went a different way, which is to try to do things radically differently. We're not saying this is the way or the only way, and probably there's a combination of all these ideas that need to be put together.
Mm-hmm. Well, just to mention what I meant is, for instance, if the drone is detecting fire, then the scale is getting smaller in time. So you have more states as you get closer to the fire than you did before, because before it wasn't that important.
No, absolutely. That's something that we discussed a lot with Gerardo Schneider, who's I can see there in the crowd. One of the things that's interesting about this iterator-based approach is that the plan doesn't know how many locations there are and how big they are and how small they are. So you could at some point decide to partition one location that's in that set with 100 new ones that are 100 times smaller, and it doesn't matter, right? So this kind of change of scale can work quite naturally together with what I was explaining.
That's true. Thank you.
Janina, next question.
Oh, okay. Thank you, Radu. A nice talk, Seb.
Hi, Jen.
Nice to see you, by the way. Hey. So my question here is quite simple, actually. So how abstract can you be in your mission specification, and how far you can go with that abstraction? I mean, okay, right. Okay, I'll let you answer. Maybe then I can complement if needed.
No, I'm not sure how to answer that question. The only thing that we can do, what we've been doing is we've been recollecting different missions from the literature, and there's a nice survey paper by Belliconi, for instance, which you've probably seen, and trying out missions of that kind, and seeing if we can move them to iterators, right? Which we have.
That's really nice, because I mean, I'm asking this because I mean, I'm starting also to play around with these very complex world. But the thing is that here you have shown one robot and kind of surveying the area and all the locations, and then now you move to other objects as well. So I was wondering these things about the communication between like robots with many skills, for example, or being a bit, let's say, extending a bit the, let's say, the complexity of the robot operations, and also to somehow making that, let's say, user from the user level, making possible to abstract some of those information.
Look, we know we have this way of doing things has limitations. For instance, one limitation is, just to give you an example, is that if you want to do things reactively to when you reach a location, you didn't say I want to go to this location, but you end up at the location. While you're trying to get to the location C3, you go through C1, and maybe there's something you should do there, and that's something we can't do because there's the notion that there's only one current location active which you're going to reason about. So these are things we can't do. There are things that we can do very naturally, like multiple drones. Well, this is a blackboard architecture, really. The locations in that iterator are all the tasks that need to be done. If you've got 3 drones, they could be pulling out tasks, each one from there. So that would be simple too. So it's hard to explore exactly what are the things that this can do and what it can't. We're working on that.
Okay, thank you.
You're welcome.
All right. Thank you very much again, Seb, for the interesting talk and for answering all the questions. And I'm sorry I cannot offer a coffee break where people would approach you with additional questions, and I would try to be the first one to come. But thank you again for the talk, and I think we all deserve a short break before the next session.
Absolutely. Thank you for listening and for the questions and for inviting me to give the talk.